Hello, this is Adam Paulson welcoming you to this Bite-Sized Bio webinar. Today's presentation is titled Back to Buffer Basics, Everything You Need to Know About Buffers, and is being presented by Thomas Warwick from Bite-Sized Bio. Thomas has a master's degree in chemistry from Loughborough University and a PhD in structural biology from the University of Nottingham. After a brief period working as a research assistant in knowledge exchange, also at the University of Nottingham, Thomas became a technician in chemical biophysics at Nottingham Trent University. In this role, he managed 2 research laboratories and provided technical and developmental guidance to students and researchers. In 2022, Thomas became a full-time content creator at Bite-Sized Bio, sharing his cross-disciplinary knowledge and research experience. As always, we'll have a question and answer session after the presentation, so please type any questions that you have into the questions box, which appears on the top right panel of your screen, and I'll put them to Tom at the end. Details of how to access the on-demand recording of this webinar will be sent to you by email shortly. So now over to you, Tom, for the presentation.
So thanks, Adam, for the introduction, and thank you everybody today for showing up and taking the time to attend this presentation, which is called Back to Buffer Basics, How Buffers Work. So here are the things we're going to cover over the course of this talk. So I'm going to start with how buffers work. I'm going to try and explain this a few different ways, and hopefully one of those will resonate with you. And then I'm going to go through how to pick the best buffer for your experiments, so some theoretical considerations and some practical considerations. I'm going to go through a reliable method to prepare buffers in the lab, the way I used to prepare them back when I worked in the lab full time. And then I'm going to go through troubleshooting some issues that might come up when you're working with buffers in the lab. And as Adam says, if you have any questions, just pop them in the box and I'll do my best to answer them at the end. But before we dive into anything, really technical, it's worth stopping to consider why buffers are important. Why should we care and bother to understand them? Well, if you think about it, there's almost nothing we do in the lab that doesn't require a specific and stable pH, which is what a buffer gives us. So here I've listed a few examples: PCR, cell culture, protein purification, gel electrophoresis, to name a few, enzyme assays, DNA purification, Western blots. They all require a specific pH to work. And the pH of our experiments and our experimental solutions dictates whether key molecules in our experiments are positively charged, negatively charged, or neutral. And this directly impacts their function and reactivity, and in turn the success of our experiments. And not forgetting, of course, that buffers are essential for life. We've got the carbonic acid bicarbonate buffer system in our blood and interstitial fluid. So I said I'm going to go through it a few different ways. I'm going to present a qualitative or verbal explanation, which should be fairly easy to understand. And then I'm going to try and explain using some graphs, which I hope are fairly intuitive to most of the audience. And then I'm going to try and tie these together by presenting a mathematical explanation. And hopefully just one of these really, really jumps out at you. But they should all reinforce each other, basically. So before diving in, let's also get familiar with pH, because that's a parameter we're going to return to a lot throughout this this talk. And just because of the way I've prepared these slides, it's also worth noting that chemists, and you may do this yourself, present concentrations of species using square bracket notation. So where you see a 10 in square brackets, that means we have 10 moles per litre of that substance. If we have 0.01 in the brackets, that means we have 0.01 moles per litre of that substance, or 10 millimolar. So pH then is simply the negative log of the molar proton concentration, H plus, here in square brackets. So that's our definition of pH. And then conversely, we can convert pH back to the molar proton concentration by taking the anti-log of this function here, or exponentiating it. So our molar proton concentration is simply 10 to the power of minus pH. This little upward pointing arrow, or caret, means to the power of. So for a solution of pH 7.5, the molar concentration is 10 to the power of minus 7.5. If the molar concentration was, if the pH was 2, then the molar proton concentration would be 10 to the power of minus 2. If the pH was 9, then the molar proton concentration would be 10 to the power of -9, or 1 nanomolar, I think that is. So pH is unitless. No logarithmic function it has any units, and it's a property of solutions. So essentially, pH puts the proton concentration on a positive logarithmic scale. So this allows us to present and manipulate numbers that are orders of magnitude different from one another simply and easily. So on to our qualitative explanation of how buffers work. So a buffer is a solution whose pH changes very little when a small amount of acid or base is added. So I'm sure that's a definition you're all aware of and something we can all agree upon. But we can go one step further. So it's a solution of a weak acid and its conjugate base, or a weak base and its conjugate acid. So I'd like just to take a moment to define what conjugate means here in this context. So if you have an acid, its conjugate base differs from it by having just one fewer proton and therefore one extra unit of negative charge. And if you have a base, its conjugate acid is different only by having one extra proton and therefore one extra unit of positive charge. Other than that, they're identical. So these two statements above, they pose two follow-up questions, right? What defines a weak acid and a weak base? And why do buffer solutions need weak acids or weak bases in order to work? So if you consult any chemistry textbook, it will tell you a weak acid or base partially dissociates when it's dissolved in water, creating a dynamic equilibrium between the products and the reactants. So we can express that generally, like I've done here on the left. So HA, which is any acid, partially dissociates into some protons and its conjugate base, A minus. And these opposing single-headed arrows denote that the reaction doesn't go to completion and it's reversible. So we can substitute in a real chemical, and we'll use acetic acid, CH3COOH. If you dissolve some in water, it will partially dissociate into some protons and its conjugate base, CH3COO minus. That's the acetate anion, which is the conjugate base in this instance. And as I said, this reaction doesn't go to completion; it's reversible, and because the equilibrium is dynamic, it can change in response to changes in external conditions, which is critical for buffers to work. Conversely, a strong acid or base fully dissociates into products and there's no equilibrium. So again, we can express that generally. HA fully dissociates into protons and the conjugate base, A minus. The double-headed arrow indicates that this reaction goes to completion and there's no dynamic equilibrium established. For example, hydrochloric acid. In solution, that fully dissociates into protons and its conjugate base, which is the chloride anion. Because it goes to completion, the reaction does not go the reverse way, and therefore this on its own cannot respond to changes in external conditions, such as the addition of more acid or more base. So I've written here, because the products and the reactants of the partially dissociated weak acid/base are in dynamic equilibrium, the concentration of the products and reactants can change in accordance with Le Chatelier's principle, where more acid or base is added. Le Chatelier's principle states, if the equilibrium of a system is disturbed by one or more of the determining factors, such as temperature, pressure, or concentration, the system tends to adjust itself to a new equilibrium by counteracting as far as possible the effect of the change. So if we add some acid to a buffer, it will react with the conjugate base, disturbing the equilibrium. So more of the conjugate acid will dissociate into protons and conjugate base to offset this change, and vice versa. So let's try and put a real chemical to this. Let's look at it in context of a real buffer system. So we can use our acetic acid system that we had earlier, which I've written here. Now let's imagine we add some acid to this buffer, or some acid is evolved during the course of our experiments. So some added acid, which I've written here in bold, will react with the conjugate base, which I've expressed as underlined. So we've got our extra protons that are evolved during the course of our experiment, or that we otherwise add to our buffer, and it reacts with the conjugate base, the acetate anion, to reform acetic acid. So how that affects the equilibrium position of our overall buffer system is initially the equilibrium position is moved off to the left, right? Because these protons combine with the acetate anion to reform acetic acid. So the concentration of this is increased as some protons are liberated. As some protons are added to our experiment or evolved during the course of our experiment. So the concentration of this increases, the equilibrium is pushed to the left initially, then Le Chatelier's principle states to offset this change, the system will try to adjust to counteract this change. So the acetic acid would dissociate back into protons and back into acetate anions to try and offset this change. Conversely, if we add some base, it will react with the conjugate acid. So we've got some base written here, OH minus in bold, hydroxide anions. They'll react with the acetic acid in our buffer system to generate acetate and some water. So in the context of our overall equation, the equilibrium is initially pushed off to the right because this reaction here generates the acetate anion. So the concentration of this is increased. Our dynamic equilibrium is disturbed. So the acetate anion will combine with some protons to reform acetic acid and try to move the equilibrium position back to where it was initially before we added any base. So a way you can think about this is the pH remains almost unchanged because the protons circled in red, these protons here involved in the overall equation, they're not consumed or liberated by any of these reactions here, right? So these protons, we've added them or they've come about during the course of our experiments. And this reaction here doesn't feature any protons. So these, or the concentration of these protons here is virtually unchanged. At some stage, however, all of the acetic acid or all of the conjugate base will get fully used up and we'll observe a drastic swing in pH, which I'm sure you've seen when preparing buffers in the lab. And this is because you've exceeded the capacity of your buffer system. So let's try and add some graphs to this then. Let's try and explain it in a more visual way. So here we're adding some acid or base to water. We've got this graph with pH on the y-axis and the concentration of our buffer acid and its conjugate base on the x-axis. So here I've got it written as HA and A minus, but in your head you could think of this as acetic acid and acetate or whatever you like. And as we add some base, the pH increases, and as we add acid, the pH decreases as we expect. And in fact, for every 10-fold addition in base, pH will go up by 1, and for every 10-fold increase in acid concentration, the pH will decrease by 1. So this is just the pH scale. Now, if we add acid or base to a buffer solution, what we can see is this perfectly linear relationship. It breaks down. It's no longer perfectly linear in the presence of a buffer. And what we can say is actually the pH change when we add acid or base to our buffer solution is proportionately reduced within certain limits within our buffering range. So this gradient becomes shallower. And unsurprisingly, what you find is the optimal conditions of your buffer, which if we agree are when it's equally capable of accounting for more acid and more base, occurs at the pH at which the concentration of your buffer acid and its conjugate base are equal, which makes sense, right? Because your buffer is equally able to compensate for more acid and more base. If we had significantly more acid concentration than conjugate base, we would be on the acidic end of our buffering range, and our buffer would have a limited capacity to counteract the addition of even more acid. And conversely, if we had significantly more conjugate base than buffer acid, we would be on the basic end of our buffering buffering capacity, and our buffer would have a limited ability to compensate for the addition of even more base. And as I marked on the graph, you get these termini where you've used up all your conjugate acid, and your pH drastically increases when you add some more base. Or here, you've used up all your conjugate base, and the pH drops off when you add more acid. I've marked on the graph pKa. Don't worry too much about this because we're going to explore it later, but it so happens that the pH at which the concentration of your buffer acid and its conjugate base are equal is the pKa of that buffer system. So in a nutshell, you've just seen that the pH is not even irrespective of the amount of acid or base added to your buffer solution. The pH change is proportionately reduced over a given range. That's the buffering range, and that's the key takeaway from that graph. So let's look at this in a slightly different way. So here we've got two graphs. We've got the percentage of buffer acid and its conjugate base concentration on the y-axis, and pH on the x-axis. And both graphs are identical in this respect. And both graphs show the change in the percentage concentration of our buffer acid, HA, as we add in some base. So the red line shows the decrease in the percentage of our buffer acid concentration as we add in, as we titrate in some conjugate base to prepare our buffer. So on both graphs, I've marked, I've annotated both graphs with two sets of black arrows, and these represent the addition of some base to our buffer system. And both graphs show the addition of the same amount of base because this vertical line or this vertical distance is the same. But what you can see is your pH change. It's not even. It's not the same for both additions of base, even though you've added the same amount of base in both cases. And actually, your pH change is bigger when you've got significantly more acid than its conjugate base. So here we're at what, 95% acid, 5% conjugate base. We add an arbitrary amount of base and we get a large pH swing. Now here we're adding some base, but we're adding it at the point where we're at perhaps 75% buffer acid and 25% conjugate base. And our pH change is smaller. And if you stare at this graph for a bit, it should become apparent that as you keep adding the same amount of base, your pH change will take a minimum value at this crossover point here, where the concentration of your buffer acid is equal to that of its conjugate base, A minus. And then as you go past this midpoint, the pH change per addition of base will start to increase again. And as we saw earlier, this point where the percentage concentration of buffer acid and its conjugate base are equal, that's the pKa of your buffer system. So the addition of equal amounts of acid/base to a buffer system causes a proportionate reduced pH change as the buffer acid concentration and its conjugate base become equal. That's the key takeaway from those graphs. So let's try and add some maths to this, dreaded maths. I'll try and keep it as simple as possible. So we can explain the behavior of buffers using the Henderson-Hasselbalch equation. And that simply states the pH of a buffer system is equal to the pKa of the conjugate acid plus the log of the ratio of concentration of base to acid, conjugate base to acid. Or simply pH equals pKa plus the log of A minus concentration divided by HA concentration. So we've already defined pH. That's the negative logarithm of the molar proton concentration. The last term is simply the ratio of the concentrations of base to acid, which is fairly simple to understand. So before going any further into this Henderson-Hasselbalch equation, let's look at pKa. So previously I described acids as either strong or weak, but in reality the strength of an acid in solution is described empirically using Ka, the acid dissociation constant. It's the ability or readiness of an acid to donate a proton, H+. So using our acetic acid buffer solution from earlier, which I've written down here, if we were to define Ka for this system, it would be the the molar proton concentration times by the molar conjugate base concentration, all divided by the concentration of the undissociated acid. Or simply, it's the ratio of the concentrations of products to reactants when we dissolve some acid in solution. So now if we imagine we're working with a stronger acid than acetic acid, Ka would be correspondingly larger. Why is that the case? Well, by definition, if it's a stronger acid, it will liberate more protons. So the molar proton concentration will increase. And therefore, the molar concentration of the undissociated acid would decrease. So this overall fraction will become larger, so Ka will become larger. So the larger the Ka, the stronger the acid. So that's Ka, but what about pKa? Well, it's simply the negative log of Ka. So you could say pKa is to Ka what pH is to molar proton concentration. So I've written that here, pKa is minus log of Ka. And you've got the inverse function. You can convert pKa back to Ka, where the acid dissociation constant, Ka, is equal to 10 raised to the power of minus pKa. So this function puts the acid dissociation constant on a logarithmic scale, just like pH does for molar proton concentration. So on the previous slide, we said the larger the Ka value, the stronger the acid. Well, following these equations, the lower the pKa, the stronger the acid. And Ka and pKa are properties of chemicals, not solutions. It's a small point, but an important one. So back to our Henderson-Hasselbalch equation then. Well, if we just stare at it for a bit, we can start to infer some key properties of buffers. One is that small dilutions of a buffer don't affect its pH. What is that? Well, let's look at this last term here, log of the ratio of the concentration of base to acid. In reality, these are both dissolved in the same flask, right? When you prepare a buffer in the lab, you dissolve some HA, some acetic acid, it dissociates into some base, but they're both in the same volume of water. So when you dilute that volume of water, both of these terms are proportionately reduced, but the ratio is invariant when you dilute it. So because the ratio doesn't change, this last term doesn't change, so pH won't change. Larger dilutions do cause changes in pH, and perhaps I can talk about that at the end. And we can also use this equation to explain why buffers work best when pH equals pKa. Remember, pKa was at that midpoint of our graphs earlier on when the concentration of HA equaled the concentration of A minus. And that's actually because, well, let's look at it mathematically. When would pH equal pKa? Well, it would do so when this last term cancels out to 0, right? Because then our equation would simplify just to pH equals pKa. Well, it so happens this last term will cancel to 0 when HA in square brackets takes the same value as A minus in square brackets, because log of 1 is 0. So when you do log of 1, you get 0, and this equation simplifies to pH equals pKa. So that's what I've written down here. This last term here cancels to 0 when the concentration of A minus equals the concentration of HA, which is what our graphs showed earlier. So just to summarize, this explains why buffers work best when pH equals pKa, because when pH equals pKa, 50% of your buffer acid has dissociated. Recall that pKa was in the middle point of the buffering range of our graphs earlier on. And then the maths aside, it makes intuitive sense because your buffer, when the buffer acid and its conjugate base are present at equal concentrations, is equally able to compensate for the addition of extra base or extra acid. So that Henderson-Hasselbalch equation is kind of abstract. So let's just chuck some real numbers in and see if we can understand it on a more intuitive level as lab scientists. So I've just written it here. Now let's imagine we're preparing 100 millimolar tris HCl buffer at pH 8.5. How much HCl would you need to add? So we've got the Henderson-Hasselbalch equation here. I've written down the terms on the right-hand side, and then I've written down everything we know. So that pH, we've set it at 8.5. pKa of tris is 8.1 at 25 degrees. You can look that up. The concentration of base we've set at 100 millimolar. So how much acid do we need? So forgive the wall of maths. I'll try and explain it briefly. Don't fall to sleep. So at the top, I've just written the Henderson-Hasselbalch equation again. And then underneath it, I've thrown some real numbers in. So pH, we've set at 8.5 equals 8.1 plus the log of the ratio of base to acid concentration. So here I've just split those terms. Here I've just taken away 8.1 from both sides. So the log of your concentration ratio of base to acid becomes 0.4, which is what I've written here. So then we need to remove the logarithm from this equation to make it more easy to work with. We can do that by taking the exponent of both sides. So the concentration of base divided by the concentration of acid is 10 to the power of 0.4, which if you do it in your calculator, that's 2.51. So now we've got something we can work with. The base concentration divided by the acid concentration is 2.51. So on this row here, I've simply multiplied by both sides by the concentration of acid term. And then on this final row here, I've what have I done? I've divided both sides by the base concentration. So anyway, our final acid concentration comes out as the concentration of base divided by 2.51. And if you follow that through, then you get 100 millimolar divided by 2.51 equals 39.4 millimoles. This has no units. Our starting concentration was in millimoles, so our answer is in millimoles. If you were to work this through in grams, your final answer would be grams. So it's worth a quick check of our answer. So 8.1 plus the log of 100 divided by 39.4 equals 8.5, which was our intended pH. But let's go just one step further. So how much would the pH change if we added 10 millimoles of HCl to our 100 millimolar tris buffer? Well, if we add 10 millimoles of HCl, it will liberate exactly 10 millimoles of protons because it's a strong acid, as we said earlier. And almost all of these extra protons will react with / be consumed by the tris base. I can explain why. We can assume that at the end if people so wish. So our 39.4 millimoles of acid becomes 49.4 millimoles of acid, and our 100 millimolar tris base becomes 90 millimoles because 10 millimoles has reacted with the extra acid extra protons evolved through the addition of the HCl. So if we sub those numbers into the Henderson-Hasselbalch equation, we get pH is equal to 8.1 plus the log of 90 over 49.4, which is 8.36. So our pH is changed by, what's that, 0.114. And you can keep going. You can keep adding 10 millimoles of HCl and measure the pH change, which is what I've done in this table here. So in the left-hand column, we've got the base concentration divided by the acid concentration. And in this right-hand column here, we've got the corresponding pH. So this is what we had on the previous slide, 90 millimoles of base divided by 49.4 millimoles of acid. pH is 8.36. We can go again, add another 10 millimoles. Our base concentration is dropped by another 10 millimoles, and our acid concentration is increased by that amount. pH drops further to 8.23. And if we go again, we arrive at this sort of special point that I mentioned earlier on. So you'll notice the pH of this solution here is 8.1. And if you remember on, I think it was 2 slides ago, the pKa of tris is also 8.1. So let's have a look at our base and acid concentrations, where you can see they're almost the same, right? We've got 70 millimoles of base, 69.4 millimoles of acid. If you remember back to those graphs, where we said the pH at which our buffer works the best is when it's equally able to compensate for the addition of base or acid, which happens to be the pKa of our buffer acid, where you can see this row here corroborates that. And if you keep going, and keep going, eventually you'll deplete all of the tris in your solution, and your pH will drop. So how much would the pH change if you added the same amount of HCl to water then? Well, 10 millimoles is 0.01 moles. If you remember, pH was the minus log of the proton concentration. So pH, if we added 10 millimoles of HCl to with some water would become minus log of 0.01, which is 2, compared to 8.36 from our imaginary tris buffer. So buffers do a great job at compensating for pH changes, so long as there's an appreciable amount of acid and base available. So some key takeaways, I'll just rattle through these. Let's get some on the screen. So buffer solutions compensate for the addition of extra protons and extra base hydroxide anions. They work best when the pH of your buffer is equal to the pKa of the buffer acid, or the conjugate acid. I didn't explain this mathematically, but the buffering range for a given buffer is approximately pKa plus or minus 1, bearing in mind that pKa scale is logarithmic. So tris, for example, the pKa of tris is 8.1, so its buffering range is 9.1 to 7.1, which is 2 orders of magnitude. The smaller the pKa, the stronger the acid. When pH equals pKa, 50% of your acid is dissociated, which gets us to this special point here, if you like, where pH equals pKa. pKa is a property of chemicals, and pH is a property of solutions. Small dilutions don't affect pH, and nor do dilutions affect Ka and pKa. But thankfully, you don't need to think about the maths because you've got these. So if you understand the Henderson-Hasselbalch equation, you understand buffers, but you never really need to break it out in the lab because thankfully we've got these. So how to pick a buffer for your experiments then, onto something that you probably find a bit more practically useful than what I've just been through. Well, there are some theoretical considerations and then some practical ways you can go about screening candidate buffers. So a key thing to bear in mind is the pH of a buffer will change with temperature. And in fact, tris and sodium phosphate buffer systems exhibit a pH change of greater than 1 when the temperature decreases from plus 25 to minus 35 degrees. So the pH increases with decreasing temperature and vice versa. Why is that? Well, the dissociation of a weak acid is mildly endothermic. It takes up some energy, or it takes energy from the universe in order to proceed. And that's because you're breaking the bond between the proton and the rest of the molecule. Even though that proton's quite labile, it still takes a bit of energy for it to dissociate away from the main parent molecule. And then according to Le Chatelier's principle, if you decrease the temperature of a reaction that's endothermic, that requires some energy to go, then you will disfavor it. So as you drop the temperature, you disfavor the dissociated form of that acid. So pH increases. Now this will matter if your experiments are at high or low temperatures. And it also matters if you intend to freeze your sample and you suspect high pHs cause aggregate formation if you're working on a purified molecule. For DNA, it doesn't really matter because DNA is rock hard. It can last for centuries, but delicate biomolecules, not so much. And you can read the full study by scanning that QR code or following that link. So everything we've said hitherto points to this rule, right? You simply pick a buffer with a pKa approximately equal to the intended pH of your experimental solutions, because that's when it will be under optimal conditions to work as a buffer. Bearing in mind, pH does change with temperature. So I've got a list of abbreviated goods buffers here. You've probably seen this chart pinned up in various labs. It's quite an old reference now, but it's still a useful one. So yeah, feel free to go and have a look. But here's some buffers in their corresponding pKa's. I believe these are for 25 degrees, but it's not actually quoted in the paper. And I guess just while I'm on this slide, it's worth explaining why pKa changes with temperature. So we've said pH will change with temperature. Therefore, Ka will change with temperature, right? Because if you remember, Ka is the concentration of the products divided by the concentration of the reactants. So if you change the proton concentration, you'll change Ka, and therefore you'll change pKa because it's simply the negative log of Ka. Then you also need to consider will the buffer interfere with your downstream experiments. So chloride absorbs light in the far UV region. It absorbs at below 250 nanometers. So, for example, if you're doing circular dichroism or any other spectrophotometric measurements in that region, you'll perhaps want to substitute your tris HCl for something like potassium phosphate, something that's free of chloride. Alkenes, carbon-carbon double bonds absorb at about 220 nanometers. That's because of the pi electrons in the double bond. They will undergo a pi to pi star transition. Maybe you've seen this when you've checked DNA concentration on the nanodrop, and you get a peak at about 220 nanometers. That is probably carbon-carbon double bonds absorbing the light. We just said the pH of tris buffers changes by about 0.03 per negative change in degree. Many phosphate salts are only moderately soluble in water and readily precipitate. Solubility is never an issue until it is. And what I mean by that is the last thing you want is buffer salts precipitating out all over your expensive purification columns and filter membranes. And then some buffers may also resemble a cognate ligand of your sample, which could be a good or bad thing. One example that leaps to mind is DNA binding proteins. Many of them are phosphorylated to enhance their DNA binding. If you're working in a phosphate buffer system, that are probably present at 10 to 100 millimolar. In any case, it'll be orders of magnitude higher in concentration than your target biomolecule, and you may find it might start to act as a non-covalent ligand. But the good news is tris and phosphate fine most of the time. So what practical things can you do to screen buffers? Well, the simplest thing is just to try some different ones and see if you notice a benefit. If you're working on a purified biomolecule and mono or polydispersity is key thing, then you could try light scattering measurements or even gel filtration, side exclusion chromatography, coupled with multi-angled light scattering. This takes the place of your UV detection, and this will measure the refractive index of your molecule and tell you its dispersity, whether it's homogeneous and in one form or whether it's in several different structural forms. But this is quite low throughput and the equipment's quite rare. One thing we do have access to is, or most of us have access to, is a qPCR machine. And this enables you to do something called the thermophore assay, also known as the thermal shift assay or differential scanning fluorimetry, which I'm just going to focus on for a few slides. So what is the thermophore assay? Well, simply you heat your target molecule up in the presence of a fluorescent dye in a real-time PCR machine, and then you use fluorescence intensity to calculate the melting point of your target molecule. The chemical environment of a target molecule will affect its melting point. And an increase in the melting point relative to a control implies your buffer or pH or whatever change you've made has stabilized it, right? So the basic principle is you heat your target molecule up in the presence of a dye called cypro-orange. As the protein or biomolecule unfolds, it will expose its hydrophobic interior. The cypro dye binds to non-specifically to hydrophobic residues, and in doing so, fluoresces. It experiences reduced fluorescence quenching. Fluorescence quenching basically means the fluorescence is reduced, and it's the water molecules that cause it for cypro. So just to illustrate this graphically, we've got this imaginary protein here in your real-time PCR machine. At room temperature, it's folded, and then as you heat it up, it begins to unfold. Some of the cypro dye molecules begin to bind to it. I've represented these in orange circles. And as you add more energy, as you increase the temperature, more cypro begins to bind, so you get more fluorescence. And you keep going on until you've got no structure left, and you've got as much cypro bound as there ever will be, and that gives you your maximal fluorescence. And the melting point will simply be the midpoint of this sigmoid here. So practically, you program your real-time PCR machine to heat the samples at about 1 degree a minute from 25 through 90 degrees and record fluorescence at or near 570 nanometers. And you do that because cypro-orange absorbs at 470 nanometers and emits at 570 nanometers. So you place your samples in the real-time PCR machine, equip it with an appropriate filter such as ROX Orange, and you press go. And you plot fluorescence counts versus temperature for each experimental condition, and you should get a sigmoidal curve that looks something like this. So here's some example data from my thesis. First, this is roughly the same until you start to unfold the protein. You get this nice sigmoidal curve, and then you measure its melting point. Generally speaking, an increase in the melting point by 1 degree indicates that your experimental condition has had a stabilizing effect. And conversely, a decrease in the melting point by 1 degree indicates a destabilizing effect. Of course, you can do as many replicates as you like to measure statistically what is significant and what isn't. But if you stop to think, this is quite a powerful assay, because you've got this 96 well format, which means you can screen lots and lots and lots of buffers and conditions in one go. And when we say buffers here, we can think about it in the narrow sense, i.e. a specific buffer molecule like tris or MOPS or HEPs, or you can mean buffers in the broader sense to encompass our entire experimental solution, including additives such as glycerol, reducing agents, different salts, and you can screen literally hundreds of conditions in an afternoon. And the assay is quite economical, requiring just 10 micrograms of protein per tube, per reaction. But remember to use clear PCR tubes and not the orange ones for obvious reasons. So if you want to dive into this a bit deeper, you can follow these references. So this will take you to a paper where people have used this assay for structural studies, so purifying proteins for X-ray crystallography. They talk you through how to do it, and then I've written a short article on Bite Size Bio that talks you through this assay and gives you a general protocol that you can adopt for your experiments, and you can use it to screen whether or not your target molecules are happy or unhappy in the presence of certain buffers and at different pHs. So just wrapping things up then. So a reliable method to prepare buffers in the lab, it's easier than you think. It's just one slide's worth of instructions. So basically get 2/3 of your final desired volume, stirring vigorously. The reason you do this is because if you add water to the salt, a lot of the times the salt will just set as a rock hard lump and you can never get the thing to redissolve again, and the magnetic stirrer bar will just bounce off it. But if you throw the powder into stirring water, it might take some time to dissolve, but at least it will go eventually. You don't have to start again. So you add your acid or base, 1 spoonful at a time, until it's fully dissolved into the stirring water. And then you simply titrate in the acid or base dropwise until you've reached your final pH. Don't let the buffer heat up or cool down too much. And prepare it at the temperature which you intend to use it for all the reasons we've said earlier. And then dilute your buffer to the final volume. And some people have asked me, does the powder that you dissolve, your 60 grams of tris, is that included in the final volume? And the answer is yes. The powder is always included in the final volume of your buffer. Troubleshooting buffer issues. I'll start us off with a few, but maybe we'll get some in the comments. So do you need to start again if you overshoot your intended pH? The answer's no, you don't, but it's probably wise to. And the reason it's wise to is if you overshoot your intended pH and then pH your buffer back to your target, you're adding more dissolved salt than you need, which could impact your experiments. For example, you're adding HCl to a buffer system and you make the buffer more acidic. So then you use some sodium hydroxide to make it more basic and get back to your intended pH. Well, when you're adding the HCl, you're adding chloride, dissolved chloride. And then when you're adding sodium hydroxide, you're adding dissolved sodium. So you've got dissolved sodium chloride in your experiment, more so than if you'd not overshot your intended pH. This might impact experiments where osmolarity and ionic strength are critical. So for enzyme assays, for example, you probably don't want to readjust your buffers if you overshoot the intended pH, because your dissolved salt concentration is then an unknown quantity. Do you need to start again if you overshoot the intended volume? Again, no, you don't, but it's probably simpler to. So as long as you know how much you've overshot by, you can simply work out how much you've diluted your components by. For example, you're preparing 500 mils of your buffer, your final volume ends up being 550 mil, well then your final volume is 110%, right, of what you started with. So accordingly, the concentration of everything dissolved in that solution is 90% of what you originally set out to prepare. So as long as you know that and you can live with the reduced concentrations of everything, it should be fine. Just remember to make a note of it. Here in the UK, buffers precipitate out of solutions all the time because the labs are cold. The solubility generally decreases with decreasing temperature. And again, phosphates are notorious for this. They're still fine to use, just make sure you re-dissolve everything before using it. Otherwise, the pH won't be as you prepared or as it was prepared. The way I used to do this was just heat things up in the shaker incubator that we used to grow E. coli, leave it for a few hours, and you come back and it's usually all redissolved. And then it should be fine. But of course, you can check the pH if you're superstitious. And then this happens quite a bit as well. You come to your buffer, you give it a swirl, and there's stuff in it. What should you do? Well, you should probably tip it away. If it's an experiment where your life depends on it, it's a really critical one. Just throw the buffer away. That floaty stuff is probably fungus. And if you think about it, right, our buffer solutions, they're usually pH to somewhere near physiological pH. And there's usually a nitrogen source and a carbon source inside them. So things love to grow. If you're in a bit of a pinch, you can just filter the buffer under a vacuum pump with a nitrocellulose filter and sterile filter it, but it won't capture everything, and you can guarantee the things will regrow. So they were the ones I could think of. With that, I'll wrap up. So here's some useful resources that I used to prepare these slides. Obviously, Wikipedia is a good go-to resource. LibreText Chemistry has some good things on buffers, and I've listed a few articles there. And then Stack Exchange, people have come up with some really good visual representations of how buffers work. So with that, I'll thank you all for listening and try to field any questions. Thank you.
Well, thank you, Tom. That was an excellent presentation.
Thank you.
So we've got a couple of questions so far from the audience.
Good.
If anyone else has a question, please feel free to pop the question into the question box on the top right panel of your screen. Okay, Tom, so going to the first question, I think one of the audience members has picked up on one of the points you made earlier. So why do large dilutions affect pH when small dilutions don't?
It's because water itself dissociates into protons and hydroxide anions, right? That's why it's got a pH of 7. And the larger the dilution, the more this affects the final pH. And that Henderson-Hasselbalch equation doesn't mathematically account for the fact that water molecules themselves dissociate into protons and hydroxide anions. So intuitively, think about it this way. If you prepare a buffer solution at pH 3, say you've got a few mils of it, and you dilute it by a few mils, the pH won't change, or it will change negligibly. If you go and tip that small phial of buffer into your bath and then measure the pH of your bath, the pH will be neutral, or whatever the pH of your bathtub is, because the self-ionization of water becomes the dominant effect, but it's not represented mathematically in the Henderson-Hasselbalch equation.
Okay, thank you. All right, and then the next question. So this goes back, I think, to an earlier example that you had with adding 10 millimolar tris to the HCl, and you said that you can assume that all the extra protons will react with the tris base. Why is that?
So this is something I didn't explain in the slides, but when we refer to Ka, we always refer to we're always referring to the buffer acid. So it's the acid dissociation constant of the conjugate acid of that system. And tris is a base, and the basic moiety is a primary amine, NH2. You dissolve that in water, you get tris NH3+. That's the conjugate acid form. So the Ka describes the dissociation of that tris NH3+ back into just normal regular tris and some protons. So the pK of that system is 8.1. So Ka is therefore 10 to the power of minus 8.1. which is like 0.000000001. So let me just get this straight. So if you remember Ka, that's the ratio of your products to reactants. Well, the product to reactant ratio is 0.0000000, however many noughts, 1, or 10 to the power of minus 8.1. So it's a really small number, which means you've got loads more reactants, basically 100 million times more reactants than products. So you've got basically 100 million times more undissociated tris NH plus than just tris and the free protons in solution. Does that make sense?
Yeah. Okay. All right. Right. Well, thanks, Tom. Um, so another question. I don't know if you can help with this one. Maybe you can clear it up. So Sandesh asks, while making a mixed phosphate buffer using the Henderson-Hasselbalch equation, what pKa do I use? I've searched the internet and I found 3 different pKa's.
So yeah, so there's another point actually. So that Henderson-Hasselbalch equation, that refers to, it's a really good question. That only refers to what you call monoprotic acids. So you've got acetic acid, right? It can give up 1 proton, whereas phosphate can give up 3. It's what you call triprotic. So you've got your phosphate atom, you've got a double bond to an oxygen, and then you've got 3, sorry, I'm not on camera, but you've got three single bonds to oxygens, and all of those, or you've got 3 single bonds to OH groups. All of those protons are labile. They can all be detached from the main phosphoric acid molecule. So you've got 3 pKa's because you've got 3 acidic moieties in phosphate, and as protons are removed, the phosphate anion becomes more basic. It's more reluctant to give up subsequent protons because it's negatively charged. A proton's positively charged, so subsequent protons get harder and harder to remove. So in terms of your question as which one should you use, it depends whether you're using mono, di, or tribasic phosphate. So when you prepare a buffer, if I remember back, you normally mix mono and dibasic forms to achieve the desired pH. So use the pKa of those, but the Henderson-Hasselbalch equation won't work for that because the Henderson-Hasselbalch equation only works for monoprotic acids. But if I don't know if we can get in touch with people after the presentation, but there are tables that show you how much sodium phosphate monobasic to prepare, how much sodium phosphate tribasic to prepare, and then at what ratio to mix them to achieve the final desired pH. It's a table I've used loads during my PhD. So if I can get in touch with Sandesh, I'll send that resource.
Okay. Right. Well,
But
Sandesh.
in short, the Henderson-Hasselbalch equation won't work, Sandesh, for phosphate because it's not monobasic, not monoprotic.
Okay, thanks, Tom. All right, this one a fairly complicated question, but I'll read it out and see how you go. So this one's from Sean. Says, any advice on buffer screening for SPR applications? I'm not quite sure what that was. Specifically, the addition of organic solvent as an additive in buffers. We've used DMSO with varying results, which is sealed and stored in a desiccator. I'm not quite.
So here you're meaning buffer in the broader sense, like I mentioned earlier, where you're including other, you're referring to the experimental solution. Unfortunately, I've never done SPR as a technique. I know what it is. It'd
We
be
could
interested
follow
to
up
know how
offline.
follow up offline. I'd be interested to know how the results are affected, what DMSO is doing or not doing. But I don't know what other organic solvents you would use for SPR because I've not done it. So I'm sorry, Sean, but I can't answer that.
Okay. All right, thank you, Tom. And I think we've got one more question here. This is a bit more practical, probably leading off the last start. So you mentioned, how temperatures affect. So what is best practice for you've spoken about preparing buffers. What about storing buffers, and how long can they be stored, without affecting their efficacy? You spoke about floating bits and that sort of thing. So
Yeah, it's kind of qualitative. If you're storing them in the cold, in the dark, well, I hesitate to say indefinitely because eternity is a long time, but let's talk of the order of your tenure, 1 or 2 years. So what I would always do is always let the buffer come back to room temperature check the pH and see if it still corresponds to what was scribbled on the side of the falcon tube, and then just give it a swirl and visually inspect it for precipitate and growth. And if the pH is it matches what is written on the side and it's clear, it's probably fine. Um, but I would say 1 to 2 years if stored in the cold and dark.
Okay, but probably always a good idea to prepare fresh buffers anyway.
Yeah, if you've got the time. If you've got the time.
Yeah. Okay. Well, Tom, look, I think that about wraps it up. Thank you very much. That was a really informative presentation and a great discussion.
Thank you.
And also thank you, the audience, for taking the time to attend and listen in. And so until next time, Tom, thank you again, and good luck, everyone, in your research, and goodbye from all of us at Bite Size Bio.
Thank you.
Thanks.